What's up, everybody? Today we're kicking off our journey into zero-knowledge cryptography. It's really starting to make waves right now and will likely be a big part of many applications and protocols in the near future, if it's not already. From authentication to bridging funds to zk rollups, zero-knowledge cryptography is making its mark on both the Web 2 and Web 3 worlds. If you're watching this series, you probably already know how huge of an impact this could have. And while the concept of zero-knowledge proofs has been around for decades, recent breakthroughs in cryptographic research, along with the growing needs of the blockchain space, have turned what was once a purely academic idea into something practical, and something that can and should be used in everyday applications. Zero knowledge has often been called moon math, suggesting it's too complicated for most people. I disagree. A lot of the material I've seen either oversimplifies things or goes so deep into the math that it's really only accessible to experts. My goal with this series is to find a balance. I want to explain the math in a way that's approachable for developers and help you build a real understanding of how zero knowledge works, so it's no longer a black box. Some concepts won't be proven with full mathematical rigor, mostly due to time, but the focus will be on intuition and the key ideas that actually matter. By starting from the basics and building step by step, the goal is to give you a clear path through the space and help you develop confidence as these ideas come together. One more caveat I want to mention is that zero knowledge can be used for a lot of different applications, but in this series, I'll be focusing primarily on how it's used in the blockchain space. In practice, that means we'll mostly be talking about zkSNARKs. If that term doesn't mean anything to you yet, don't worry, we'll get into it shortly. Now, what are the prerequisites to this video series? To get the most out of this video series, I'm going to assume that you have an understanding of the following: group theory, elliptic curve groups, and elliptic curve pairings. If you don't feel comfortable with these, please watch my Demystifying Cryptography Fundamentals for Developers 3-part series linked here before coming back to this series. Furthermore, I'm going to assume that you know what a polynomial is and also can do basic linear algebra like matrix multiplication. If you fulfill all these prerequisites, then without further ado, let's get right to it. Today, we're going to spend some time on fundamentals and definitions. I know this isn't the most exciting part, but having a strong foundation here is really important before we move on to the actual protocols. So to get started, in order to understand what a zero-knowledge proof is, we first need to talk about what a proof system is. A proof system involves two parties, a prover and a verifier. The prover's job is to convince the verifier that a statement is true by providing a proof. The verifier's job is to check that proof and then either accept it if it's valid or reject it if it's not. To make this more concrete, what are some examples of statements? Well, a statement could be the equation w cubed minus 4w squared plus 9w equals 10 has a real solution. Or the Sudoku puzzle has at least one valid solution. Or some more practical real-life examples. This passport has a valid digital signature. Given a program and an execution trace of the program, the trace follows the instruction set rules. For simplicity, let's focus on building a proof system for the first example, where the statement is that the equation w cubed minus 4w squared plus 9w equals 10 has a real solution. Since the prover's goal is to convince the verifier that the statement is true by sending a proof, what could they actually send as the proof? One simple approach would be for the prover to just send the solution itself, w equals 2. The verifier could then check this by plugging in the value and verifying that 2 cubed minus 4 times 2 squared plus 9 times 2 equals 10, and be convinced that the statement is true, meaning the equation really does have a real solution. Using this example, we can see two key properties of a proof system: completeness and soundness. Let's break down what these mean. Completeness, in simple terms, means that an honest prover will always be able to convince an honest verifier. In our example, this proof system satisfies completeness because an honest prover will always send the actual solution, w equals 2. When the honest verifier plugs this value into the equation, they'll see it works and accept the proof. In other words, completeness ensures that if everyone is honest, the valid proof will always be accepted. Now, what about soundness? Simply put, soundness means that a dishonest prover can only convince an honest verifier with a super low, basically negligible probability, or sometimes not at all. In other words, a malicious prover shouldn't be able to fool the verifier. Our example proof system satisfies soundness. For instance, if a dishonest prover tried to send w equals 3 as a solution, the honest verifier would plug it into the equation and see that 3 cubed minus 4 times 3 squared plus 9 times 3 equals 18, which is not 10. Since it doesn't work, the verifier would reject the proof. So intuitively, what completeness and soundness are saying is this. An honest verifier will always accept a valid proof, which comes from an honest prover, and it will always, or almost always, reject an invalid proof, which comes from a dishonest prover. And a proof system must satisfy both completeness and soundness. In this series, our goal will be to design proof systems that clearly define three things: what the prover does, the proving algorithm, what the proof itself looks like, and what the verifier does, the verification algorithm. In our simple example, the prover's algorithm is straightforward if they already have the solution. The proof is just the solution itself, and the verification algorithm is to simply plug in the proof and check that it works. Later in the series, the proof systems we design will be more complex, but the same three components will always apply. Okay, so if a proof system has both completeness and soundness, it already counts as a valid proof system. But we can also add a third property, an optional bonus that some proof systems have, the zero-knowledge property. If a system has this property too, we call it a zero-knowledge proof system. Zero-knowledge basically means that after the interaction, the verifier learns nothing, except whether the statement is true. In our example, if the prover just sends w equals 2, that reveals the actual solution, so it's not zero-knowledge. The verifier learns more than just the truth of the statement. The big question is, can the prover send some other kind of proof, something that isn't just the solution, where the verifier can still check it and accept and reject correctly? The answer is yes, and it's going to be really interesting. In fact, designing these kind of proofs is exactly what we'll be doing for the rest of the series. Now notice something interesting. Completeness and soundness protect the verifier. These properties make sure the verifier can't be tricked if the prover is dishonest. On the other hand, the zero-knowledge property protects the prover. Even if the verifier is malicious, they can't learn anything from the proof the prover sends. Think of it like logging into a website. You're the prover and the website is the verifier. The website needs to check your username and password and only let you in if you're really you. This protects the website from letting in the wrong people. But what if the website is malicious, like a phishing site? It could try to steal your password if you enter it in. A zero-knowledge proof changes the game. Instead of sending your actual password, you send a proof that convinces the website you are who you say you are without revealing your password at all. That way the malicious site won't be able to learn your password and you'll stay safe. We need to go through a few more definitions that will be important for the rest of the series. I think the easiest way to explain them is with an example. So let's now say a prover wants to convince a verifier that the equation w squared minus 4w plus y equals 0 has a real solution. Now imagine we want to write the computation of the left-hand side of the equation as a series of simpler equations. Each step can have only one addition, subtraction, or multiplication. We can also define new intermediate variables to help. Here's how we could break it down. W times w equals w2, w2 minus 4w equals w3, w3 plus y equals w4. Take a moment to look at this. What we've done is simply split the original equation into smaller pieces and define intermediate variables w2, w3, and w4. If the correct values for w and y are provided, and the steps are computed correctly, w4 will equal w squared minus 4w plus y. Can you see that they're equivalent? This set of equations that defines the computation is called a circuit. Now remember, in a proof system, we don't automatically trust that the prover gave the right values or even did the computation correctly. So what do? We define constraints that both the prover and the verifier agree upon. This is super simple once we have the circuit. Using our example, the constraints are just the same equations we wrote, plus one more, which is w4 equals 0. Imagine both the prover and verifier have this set of constraints. They've agreed upon them ahead of time. What this means is that if the prover can provide values for w, w2, w3, w4, and y, such that all of the constraints hold, the verifier can be convinced that the statement is true. In other words, the prover has successfully shown that the equation w squared minus 4w plus y equals 0 has a real solution. You might be wondering why we even bother breaking a bigger computation into these smaller equations. I'll get into that in later videos when we dive into the math. But for now, just know that this step is necessary if we want to build the zero-knowledge proofs that we're aiming for. I also wanted to make a quick distinction between circuits and constraints, because it helps to keep the ideas clear. In industry, people often say things like, I'm coding circuits or I'm developing circuits, but most of the time they really mean they're coding the constraints. Making the distinction up front just helps us avoid confusion as we go deeper into the series. Similar to our previous example, you might think the prover's proof would just be the solution itself. So in our example, the values of w, w2, w3, w4, and y. That's possible, but like I mentioned earlier, this would not be zero knowledge, since the verifier learns all these values. Later in the series, we'll develop the math that lets us keep values secret while still convincing the verifier that the statement is true. Once we have those techniques, the prover and verifier can agree beforehand which values will be private and which will be public, just like they agree on the constraints. For example, they might agree that w, w2, w3, and w4 are secret, while y is public. The secret values are called witnesses. Think of them as secret inputs. And the public inputs are just that, public. Sometimes there is only one witness and public input that satisfies the statement. However, in some cases, there are multiple sets of witnesses and public inputs that do. One term you might hear is the term relation. This means all sets of witnesses and public inputs that satisfy the statement. One more term you might hear is witness extension. Often the prover can take part of the witness, like w in our case, and then compute the other witness values w2, w3, w4 automatically. That computation is called witness extension, basically filling in the rest of the witness from the partial input. Hang in there. We've made it past the toughest part of the definitions, and we just have a few more to go before we wrap up. We've talked about zero-knowledge proof systems, but what exactly is a zkSNARK? Well, zkSNARK is an acronym that stands for Zero Knowledge, Succinct, Non-Interactive, Argument of Knowledge. And let's break down what each of those words actually means. Let's start with succinct. For a proof system to be succinct, two things need to happen. The proof has to be short, and the verification time has to be fast. But how short and how fast? In formal terms, we say that the proof should be sublinear in the witness size, and verification time should be sublinear in the circuit size. Basically, the proof size and verification time shouldn't grow linearly as the problem gets bigger. Let's look at our previous example, the equation w squared minus 4w plus y equals 0. We designed a proof system where the proof was just all the values w, w2, w3, w4, y. And the verification algorithm was just to plug all these values into the equations and check them. This system is not succinct. Why? Because if the equation gets more complicated, for example, if we added w cubed into the equation to make it w cubed plus w squared minus 4w plus y, we'd need to add another intermediate variable, w5, to the proof. And if we added a w to the fourth term, we'd need to add a w6 to the proof. So we are sending more and more witness values as the equation grows. The proof size grows linearly with the computation. And since the verification algorithm is plugging in these values to check, it also takes longer and longer to perform. And actually it increases linearly too. A truly succinct proof, on the other hand, stays small and can be checked really quickly, even as the computation gets huge. There's an even stronger version of succinctness called strongly succinct. We further restrict the growth of the proof size and the verification time to not just be sublinear, but to only grow polylogarithmically with the circuit size. In simpler terms, even if the computation is huge, the proof stays tiny and the verifier barely has to do any work. In this series, that's exactly what we're aiming for. It's super powerful because in real-world applications, you often want the verifier to do very little work, while still being able to check that a massive computation was done correctly. Keep in mind that while succinctness is only about proof size and verification time, we still care a lot about the prover's speed in practice, the prover algorithm. Ideally, we want the prover to be as fast as possible, and there's plenty of research focused on making provers more efficient. But just to be clear, succinctness itself doesn't say anything about prover time. It's really all about keeping the proof small and the verification fast. So technically, a proof system with a slow prover could still qualify as a zkSNARK. Okay, let's move on to non-interactive. This just means the prover sends one proof to the verifier, and the verifier can check it locally and either accept or reject it. This is different from interactive proof systems, where the prover and verifier go back and forth, sending multiple messages and proofs before the verifier makes a decision. There's something called the Fiat-Shamir transform that can turn certain interactive proofs into non-interactive ones. We'll cover that in a later video. For now, just know that our goal is non-interactivity, especially in blockchain applications. Think about it. Our blockchain is the verifier. A user submits a transaction containing a proof, the blockchain verifies it, and then acts based on whether it's valid or not. There's no back and forth here, just one transaction, the blockchain processes it, and that's it. Now let's talk about the argument of knowledge property. We've already covered soundness, which basically ensures that an honest verifier can trust that a statement is true if the proof checks out. But there's an even stronger version called knowledge soundness. Without getting too deep into extractors and all the technical details, knowledge soundness means that not only is the statement true, but the prover actually knows the witness. In other words, it's not enough that a solution to the equation exists. We care that the prover actually knows what that solution is. When we say a proof system has the argument of knowledge property, that's exactly what we mean. It satisfies knowledge soundness. And in this series, we'll be aiming to design proof systems that have this property. Now, a proof system that's succinct, non-interactive, and has an argument of knowledge, even without zero knowledge, is called a SNARK. In this series, we're going to start by building these, and honestly, this is where most of the difficulty lies. Once we've got that down, we can make a few adjustments to add the zero knowledge property and turn our SNARK into a zkSNARK. I want to point out that even a SNARK without zero knowledge is still incredibly useful, especially in blockchains, thanks to the succinctness property. That means the proof is tiny and the verification time is really fast, no matter how big the computation is. So even if the proof doesn't hide any information, it can still save a lot of time and space when verifying transactions or computations on chain. In situations where privacy isn't the main concern, but you just want to quickly check that someone did a big computation correctly, like verifying the results of a complicated calculation, SNARKs are super handy. That's it for now. Today we got a solid introduction to the ZK series. We've covered what a proof system is, including the key properties of completeness and soundness. We also saw that a special type of proof system can have a third property, zero knowledge, which turns it into a zero knowledge proof. On top of that, we went through definitions like circuits, constraints, witnesses, public inputs, and more. And finally, we unpacked the acronym zkSNARK and what it actually means. We've covered a lot of ground today, so I recommend taking a moment to make sure you really understand these terms before moving on. They'll come up over and over again in this series. That's it for now. I hope you stick around for the rest of the series. See you next time.